Welcome, everyone, to a very special deep dive edition of Leading Edge AI Radio. I'm absolutely thrilled to have you here with us today.
It's great to be here.
Before we jump into I'm looking at a massive stack of research sitting on the desk right now, but before we get into that, I do want to give a quick shout out to our sponsor, Leading Edge Fiber and Recycle.
They're doing great work.
They really are. And just as our sponsor is out there doing the hard, essential work of recycling physical infrastructure to build a more sustainable future, today's deep dive is really about recycling our outdated ideas. Good morning, and welcome to the deep dive. If you are grabbing your coffee right now, maybe you're heading out for a run, or you're just settling into your morning commute, I need you to lock in.
Absolutely lock in.
Because the tempo today is fast, the stakes are unbelievably high, and the numbers we are about to throw at you, well, they are going to fundamentally restructure how you view the entire tech sector.
It really is a massive paradigm shift.
It is. We are looking at a stack of intelligence from 2025 and 2026 that completely shifted my perspective on where the global economy is actually heading.
Same here. It's eye-opening.
We have financial blueprints from Morgan Stanley, heavily detailed architectural breakdowns from Introl and Intuition Labs, Wikipedia updates tracking real-time supply chain shifts, and some incredibly dense strategic analysis from McKinsey and RCR Wireless.
Heavy reading, but incredibly important.
Right. And our mission today, we are going right into the trillion-dollar engine room of the future to completely demystify the economics of artificial intelligence.
So we are bypassing the software hype entirely today.
Exactly. We are looking at the raw, physical reality, an unprecedented investment race, the brutal cloud wars playing out over custom silicon, and how this digital ambition is violently colliding with the physical limits of our planet. Okay, let's unpack this.
It really is a physical collision, and I think grounding the conversation in that physical reality is exactly the right approach for you listening today.
Yeah, because we don't usually think of it that way.
Right. We are so accustomed to viewing AI as this, ephemeral cloud service or a clean API endpoint on your phone. But what these reports expose is a staggering terrestrial arms race.
Terrestrial. I love that word for this.
Because it is. We are talking about concrete, copper, silicon, and high-voltage transmission lines. This is a hardware and financial mobilization driven by the absolute unforgiving necessity of scaling laws.
It's physical infrastructure.
Exactly. The digital world is currently slamming into the thermal and electrical limits of the physical world, and the sheer scale of capital required to push past those limits is dismantling traditional economic models across multiple industries.
So let's start right at the poker table. Because I was looking at the Morgan Stanley capital expenditure projections for the hyperscalers, and I genuinely thought there was a typo in the spreadsheet.
I had the exact same reaction the first time I saw those charts.
The buy-in for this game has completely decoupled from anything we've seen in modern corporate history. Let's look at the 2025's scoreboard.
Let's do it.
Amazon is projecting $100 billion in CapEx.
Staggering.
Microsoft is at $80 billion. Alphabet is forecasting $75 billion. And Meta is sitting somewhere between $60 and $65 billion.
Just massive, massive figures.
You aggregate that, and it is $315 billion in a single year from just 4 entities.
4 companies.
And that doesn't even factor in the OpenAI-led project Stargate, which is a $500 billion blueprint spread over 5 years.
Right. Stargate is its own entire ecosystem of spending.
$315 billion in 12 months. You are looking at the gross domestic product of a country like Finland or New Zealand, entirely liquidated and poured into server racks and cooling systems.
It's the GDP of a developed nation.
How does Wall Street even process an infrastructure build of this magnitude without absolutely punishing these companies for their free cash flow burn? I mean, normally investors would revolt.
Well, they process it because the alternative is complete obsolescence.
Yeah.
But to your point, it completely shatters the historical comparables.
Right.
If you look back at the telecom fiber build-out in the late 90s, or even the early days of the 4G LTE network rollouts,
Which were huge at the time.
they were massive. But the capital intensity as a percentage of revenue wasn't anywhere near what we are seeing from these 4 companies right now. The market is tolerating this extreme capex because they are looking at the same math the hyperscalers are looking at.
Which is Sam Altman's 3 rules of AI economics.
Exactly. This isn't speculative in the way the dot-com boom was. It is heavily deterministic.
Right, because the scaling laws aren't just a theory anymore. They are an empirical reality.
The math checks out.
Altman's first rule states that intelligence basically equals the logarithm of the resources used. We know that transformer models don't just magically get better through algorithmic cleverness alone.
No, they
They
don't.
require a brute force, exponential increase in compute and data to achieve linear gains in capability.
And that exponential requirement for compute leads directly into his second rule, which is where the economics get aggressively paradoxical.
Tell me about the paradox.
Well, he notes that the cost to use a given level of AI falls about 10x every 12 months.
Okay, so it gets cheaper to use.
Right. Now, traditional supply and demand might suggest that as something gets cheaper, the overall capital outlay might stabilize. But in this specific context, it triggers a massive Jevons paradox.
A Jevons paradox. Explain that for the listener who might not be familiar with that economic term.
Sure. A Jevons paradox happens when technological progress increases the efficiency with which a resource is used, but the rate of consumption of that resource actually rises due to increasing demand.
Ah, I see.
So because the cheaper the inference becomes, the more ubiquitous the integration becomes.
You aren't just using it for niche data analysis anymore. You are running it on every single background process, every customer interaction, every single line of code generated.
Exactly. The efficiency doesn't reduce the demand. It pours gasoline on it.
That makes total sense.
The Jevons paradox ensures that as the per token cost approaches zero, the aggregate consumption of compute approaches infinity. Which brings us to the third rule.
The value creation.
Right. The socioeconomic value of linearly increasing intelligence is super exponential.
Super exponential, meaning it just goes entirely off the charts.
Right. If a hyperscaler achieves an artificial intelligence that is even marginally more capable, say, a model that can autonomously navigate complex, multi-step financial audits rather than just drafting the executive summary,
It's just a huge leap in utility.
massive. The value capture across the global economy for that capability is so vast that spending $100 billion to get there first isn't just justified, it is a fiduciary mandate.
You literally have to spend the money or you are failing your shareholders.
Exactly.
But I want to push back on the actual mechanics of how this is being funded because the Wikipedia sourcing on the financial structuring looks incredibly high risk.
It is definitely aggressive.
I get that Amazon and Microsoft have the fortress balance sheets to absorb this, but we are seeing this wild west of finance spring up around the secondary players.
The alternative funding structures?
Let's talk about the neoclouds and the special purpose vehicles, or SPVs. You have Morgan Stanley structuring a $30 billion deal for Meta's Hyperion data center project using Blue Hour Capital and PIMCO bonds.
A classic infrastructure offtake agreement.
But Meta isn't even borrowing the money directly. They are using an SPV to keep the massive debt off their primary balance sheet.
Applied to digital compute, yes. And it highlights a critical shift in risk allocation. By establishing an SPV, the megacorporation effectively signs a long-term lease for the compute capacity. This guarantees the cash flow for the private equity firms and the bondholders who are funding the actual concrete and silicon.
So the risk is shifted to the SPV, but the hyperscaler gets the guaranteed hardware.
Exactly. But the more fascinating financial engineering is happening with the neoclouds you mentioned, like CoreWeave.
CoreWeave is exactly what I wanted to ask about.
Yeah.
Because this blew my mind. They took out $12.4 billion in debt from private credit firms, alongside massive institutional players like JP Morgan Chase and Goldman Sachs.
A massive, massive credit facility.
And the collateral for that $12 billion loan wasn't real estate. It wasn't intellectual property.
No, it wasn't.
It was actual NVIDIA GPUs.
Yeah.
They collateralized silicon chips sitting in a server rack. How on earth does a bank underwrite a multi-billion-dollar loan against hardware that is subject to Moore's law?
That is the defining question of this specific credit cycle. If we connect this to the bigger picture, collateralizing GPUs is fundamentally different from collateralizing an office building or a commercial jet.
Totally different asset classes.
Right. An office building has a terminal value. A commercial jet has a 30-year lifespan. The useful top-tier lifespan of a machine learning GPU running at maximum utilization is intensely debated, but it is generally modeled anywhere from 1 to maybe 5 years.
5 years at the absolute maximum.
And then it is completely superseded by the next generation's price-to-performance ratio.
Right. If I take out a mortgage on a house, the house is still going to be a house in 10 years. If CoreWeave takes out a loan against an H100 cluster in 3 years, that cluster is essentially legacy hardware.
It can't competitively train the newest frontier models.
Exactly. The depreciation curve is a cliff. If the demand for mid-tier inference drops, or if there's a sudden breakthrough in algorithmic efficiency that lowers the compute requirement,
The value of that collateral evaporates.
it feels like an incredibly high-wire financial act, vulnerable to a massive margin call if the music stops.
And that vulnerability is exactly why market concentration is accelerating so violently. The structural reality of these capital requirements is creating an impenetrable economic moat.
You can't just be a scrappy startup in a garage anymore.
You absolutely cannot have a startup simply decide to compete at the infrastructure layer anymore. The minimum viable product to enter the foundational model training space requires access to gigawatt-scale data centers and tens of thousands of top-tier GPUs.
It's table stakes now.
Only the hyperscalers, heavily backed sovereign wealth funds, and incredibly leveraged neoclouds can sit at this table. The infrastructure layer of the next decade's economy is being locked down right now by a fraction of a percent of the market.
Which means for you, the listener, the underlying rails of whatever industry you work in, whether that's medicine, law, logistics, or media, are going to be wholly owned and operated by a four-player oligopoly.
That is the practical reality.
So if the minimum blind at this poker table is $30 billion, I want to know what exactly they are buying. Let's step inside the actual AI factory. Because looking at the transition from NVIDIA's Hopper architecture to the new Blackwell generation, the leap in sheer throughput is absurd.
What's fascinating here is the architectural philosophy shift. The Intuition Lab's deep dive on Blackwell versus Hopper is incredibly revealing.
Break down the difference for us.
Well, the Hopper H100, which defined the 2023 and 2024 boom, was an exceptional, versatile piece of hardware. It handled traditional high-performance computing, complex physics simulations, and generative AI.
A jack of all trades, relatively speaking.
All right, but the Blackwell generation, the B200 and the GB300 superchips, are explicitly and aggressively optimized for massive trillion-parameter transformer models. They abandon some of the broader generalized compute focus to entirely maximize generative throughput.
The specs reflect that singular focus. We're looking at fifth-generation tensor cores, 288 gigabytes of HBM3 memory, and this aggressive push into ultra-low precision modes.
The FP4 and FP6 modes.
Right. Now, for the audience tracking this, we all know the Hopper pushed roughly 4 petaflop PS. Blackwell pushes about 9 petaflop PS in FP8.
Which is already a massive leap.
It is. But if you drop down to that FP4 mode, it doubles to 18 petaflop PS. My question is about the viability of that FP4 drop. If you are compressing the precision of the calculations down to a 4-bit floating point, aren't you severely compromising the model's accuracy?
It's a great question.
I mean, how much precision can you strip away before the hallucination rate becomes totally unacceptable?
That is the core debate in quantization right now. What the industry has discovered and what Blackwell capitalizes on is that massive neural networks are remarkably resilient to lower precision during inference and even during certain phases of training.
So they don't need perfect math to guess the next word.
Exactly. You don't need FP64 or even FP16 precision to calculate the probability of the next token in a natural language sequence. The network's sheer scale compensates for the micro-inaccuracies of the lower precision weights.
Oh, that is fascinating. The scale covers up the lack of precision.
Right. By utilizing FP4, NVIDIA is trading mathematical exactness for raw bandwidth and throughput. It allows the chip to move vast amounts of data through the memory bus significantly faster.
So it's a calculated sacrifice. You accept a negligible drop in deterministic accuracy to literally double your processing speed.
Which, when you are renting these chips by the hour, fundamentally alters the unit economics of inference.
And the scale at which Microsoft is deploying this is just breathtaking. The reports detail Azure deploying a 72-rack NVL72 cluster.
A monster of a machine.
That is 4,608 GB300 GPUs, interconnected over a massive copper backplane to act as a single, unified accelerator. They are hitting 92.1 exaflop PS.
Exact-scale computing used to be a decade-long national laboratory goal. You would have massive government grants trying to hit that number.
And now you can just rent it.
Now it is a commercially available rack deployment. 92.1 quintillion operations per second.
I can't even picture a quintillion.
It's almost unimaginable, but that kind of synchronized compute power allows you to serve trillion-parameter models in real time at a cost basis that the previous generation couldn't come close to.
But there is a massive, unavoidable physical tax for hitting 92 exaflop PS. And this is where the intro blog really sheds light on the crisis going on inside these facilities, the thermal kife.
The heat problem.
Traditionally, we're used to seeing data center racks drawing maybe 10 to 15 kilowatts, with high-density GPU racks pulling maybe 20 to 30 kilowatt.
That was considered extremely hot just a few years ago.
Right, but a single Blackwell chip is pulling 1,200 to 1,500 watts on its own. When you densely pack them into an NVL72 cluster, you are generating an astronomical amount of heat.
You are effectively building an industrial furnace that happens to do math.
An industrial furnace that does math. I love that.
It's true. And this brings us to a hard, unforgiving limit in fluid dynamics and thermodynamics. For the entire history of commercial computing, data centers have relied on air cooling.
Big fans blowing cold air.
Massive CRC units pushing chilled air through raised floors and down the server aisles. But the intro analysis explicitly states that air cooling completely fails at exactly 41.3 kilowatts of power per rack.
I found that specific number fascinating. Why 41.3 kilowatts? Why is that the terminal velocity for air?
It comes down to the volumetric heat capacity of air and the physical space available in the server chassis. Air is actually a terrible conductor of heat.
Really?
It is. To remove more than 41 kilowatts of heat from a standard rack footprint using air, you have to push so much volume at such a high velocity that you cross a threshold of acoustic and mechanical chaos.
Acoustic chaos, meaning it gets loud.
Extremely loud. The fans have to spin at RPMs that generate decibel levels equivalent to a jet engine.
And it's not just about the noise deafening the technicians walking the aisles, right?
So the noise actually becomes a structural hazard.
Right. The acoustic vibration from fans pushing that kind of air volume actually starts to physically degrade the hardware. You get microfractures in the solder joints on the motherboards just from the sustained acoustic resonance.
Exactly. The sheer mechanical force required to move that much air physically destroys the equipment you are trying to cool. Air cooling past that threshold is not an engineering challenge. It is a physical impossibility.
Which forces the entire industry into a massive, heavily capital-intensive paradigm shift, direct-to-chip liquid cooling.
Liquid cooling is the only way forward for these density levels.
And the retrofitting costs are brutal. Microsoft reportedly spent $1 billion retrofitting existing facilities because they realized mid-stride that their air-cooled infrastructure would literally melt under the GPT training workloads.
$1 billion just on plumbing.
The intro report cites the cost of liquid cooling retrofits at between $2 million and $3 million per megawatt. When you are standing up a 500 megawatt or a gigawatt facility, the plumbing alone is a multi-billion-dollar line item.
It is an immense upfront capital expenditure. You are running specialized coolants, manifold systems, and secondary heat exchangers directly to the silicon heat spreaders.
You have to do it.
It is financially mandatory, not just for operational stability, but for asset protection. The report brings up the Arrhenius equation, which is critical here.
The Arrhenius equation. Break that down for us.
In physical chemistry, it relates the rate of a chemical reaction to temperature. But in microelectronics, it translates to a very established rule of thumb. For every 10 degrees Celsius, you reduce the operating temperature of a component, you effectively double its operational lifespan.
For every 10 degrees, you double the life of the chip.
Exactly.
Which ties perfectly back into the financial engineering we were talking about earlier, with CoreWeave and the SPVs.
The loan collateral.
Yes. If you have $12 billion in debt secured by these chips, you absolutely cannot afford early silicon degradation from thermal throttling. That $3 million per megawatt plumbing bill is essentially an insurance policy to ensure the collateral actually survives the duration of the loan.
Precisely. Liquid cooling handles 100 to 200 kilowatts per rack effortlessly compared to air. It drastically reduces the facility's power usage effectiveness, or PUE, cutting the parasitic energy loss from massive fan arrays.
So it saves power in the long run.
So the hyperscalers absorb the massive CapEx hit on the liquid loops because the operational expenditure savings, combined with doubling the lifespan of their depreciating assets, is the only mathematically viable way to run these facilities.
So if NVIDIA is producing these incredibly dense, incredibly hot, highly specialized chips and dictating the architectural layout of the data centers down to the cooling manifolds, how do the hyperscalers actually protect their margins?
It's the multi-billion-dollar question.
Right. If you're Amazon, Google, or Microsoft, how do you prevent your entire business model from becoming a low-margin pass-through mechanism where all the real profit gets funneled directly to Jensen Huang and NVIDIA? Because right now, NVIDIA's gross margins are historic.
They protect their margins by staging a silicon rebellion.
A silicon rebellion.
This is the underlying cloud war that is defining the next phase of the infrastructural build-out. The hyperscalers cannot allow a single vendor to maintain monopolistic pricing power over their core operational costs.
They have to build their own.
Right. AWS, Google Cloud, and Microsoft Azure are all aggressively deploying highly specialized custom silicon. AWS is arguably the most aggressive here, leveraging their 2015 acquisition of Annapurna Labs to design the Trainium and Inferential lines.
And AWS is not just dabbling in this to have leverage in contract negotiations. They are deploying this at a terrifying scale. Let's look at Project Rainier.
The Indiana facility.
Yes. Amazon activated a 1,200-acre facility in Indiana in late 2025. 1,200 acres. That is a massive physical footprint.
It's a small city of compute.
They poured $11 billion into this specific project, and it is entirely populated by roughly 500,000 of their own Trainium 2 chips. It is explicitly designed as the world's largest non-NVIDIA AI cluster, purpose-built to train Anthropic's Claude models.
The economics driving Project Rainier are absolutely ruthless. The initial data breaks down the pricing parity, or lack thereof. Historically, an NVIDIA H100 instance commanded a massive premium.
Sure.
But AWS is heavily subsidizing and aggressively pricing their custom silicon. A Trainium 2 instance was priced at roughly $4.80 per hour.
Okay, $4.80 an hour.
To prevent mass migration off their GPU instances, AWS actually slashed the rental pricing of their NVIDIA H100 clusters by 44% in 2025, dropping them to between $3 and $4 per hour.
Wait, let's look at the math there. If Amazon is slashing the rental prices by 44% on NVIDIA hardware that they already paid top dollar to acquire, aren't they just eating massive sustained losses on those racks?
Yes.
How does this custom silicon strategy actually benefit them if it immediately cannibalizes their own GPU revenue stream?
It's a loss leader strategy designed to force a broader market correction. Yes, they take a severe short-term margin hit on the H100 instances, but by aggressively pricing Trainium 2, they are forcing developers into the AWS silicon ecosystem.
It's about lock-in.
Exactly. Once a developer optimizes their stack for AWS's Neuron SDK rather than NVIDIA's CUDA platform, AWS achieves vendor lock-in on a much lower cost basis. AWS claims Trainium 2 delivers 30 to 40% better price to performance than equivalent GPUs. They are willing to bleed on the NVIDIA instances to break the CUDA monopoly and secure long-term margin dominance on their proprietary chips.
It's a brutal war of attrition. And the optimization isn't just happening at the fabrication plant. It's happening deep in the software stack.
Software optimization is huge.
The Microsoft 2020 Sustainability Report highlighted this trend years ago, and it has only accelerated. We are seeing algorithmic breakthroughs like the weightless parsec algorithm, which identifies optimal neural network architectures using 100 times less compute cost.
The software optimization is really the unsung hero of the margin wars. Innovations like Microsoft's factorized neural layers allow developers to drastically reduce the parameter count and memory footprint of a model without degrading its performance.
Because you can't just keep adding more chips forever.
Exactly. Hardware scaling is reaching physical and financial limits, so the hyperscalers are aggressively optimizing the compilers, the parallelization techniques, and the model architectures themselves to extract maximum utilization from every cycle of compute, regardless of whether it's running on an NVIDIA GPU or a Google TPU.
Okay, here's where it gets really interesting. We've covered the capital expenditure, the chip architectures, the thermal physics, and the cloud pricing wars.
A lot of ground covered.
But none of this compute matters if the nodes can't communicate instantaneously. Let's talk about the physical sprawl and the logistics of actually wiring this massive infrastructure together. The fiber optic nightmare.
The sheer density of connectivity required inside an AI factory is a logistical crisis. The IE802 data models the evolution of fiber density, and the trajectory is staggering.
How bad is it?
A standard 72 GPU AI node requires 4 times the fiber cabling of a 32 GPU node and 16 times the fiber of a traditional pre-generative AI cloud server.
16 times the cabling.
We are talking about data center aisles, where the racks are literally obscured by a solid, impenetrable wall of yellow fiber optic cabling. Managing the bend radius, the splicing, and the physical weight of that cabling is an engineering nightmare.
And the problem isn't just the physical volume of the cables, it's the limitation of the medium itself. We are actually hitting the physical speed limit of glass.
The speed of light in silica.
Right. In a standard silica fiber optic cable, light travels roughly 30 to 40% slower than it does in a perfect vacuum. When you are training a distributed model across tens of thousands of GPUs, a latency penalty of a few microseconds compounds across millions of parameter updates, resulting in days or weeks of lost training time. And time is quite literally billions of dollars.
Which is driving the intense commercialization of hollow core fiber, or HCF.
Hollow core fiber.
In a hollow core fiber, the optical light pulse travels through a microscopic air or vacuum core running down the center of the cable rather than propagating through solid glass. Because light travels nearly 50% faster in air than in silica, HCF drastically reduces the latency penalty.
But I imagine the manufacturing and deployment of a hollow piece of glass has to be incredibly delicate compared to solid glass. Are they facing issues with physical fragility or signal attenuation over longer distances?
They absolutely are. Splicing hollow core fiber requires immense precision to avoid collapsing the microstructured cladding. And historically, it suffered from higher attenuation, meaning signal loss over long distances, compared to ultra-pure silica.
So it's hard to work with.
Very. But the hyperscalers are pouring R&D into solving this because the latency reduction is mandatory for geo-distributed AI. If environmental or grid constraints force you to build your compute clusters across multiple different states, those clusters must communicate as if they are in the same room. Hollow core fiber is the critical enabling technology that allows for that geographic disaggregation.
And this massive demand for bandwidth is spilling out of the data centers and into the oceans. The RCR wireless analysis on the subsea cable market is fascinating. For decades, the global subsea cable infrastructure was built and owned by massive telecom consortiums and traditional wholesalers, who then leased capacity to internet service providers.
The traditional model.
But the hyperscalers are completely upending that market.
Because the AI traffic volumes are so immense, they can no longer rely on wholesale capacity. The hyperscalers, Google, Meta, Microsoft, are now the primary financiers and builders of transatlantic and transpacific subsea cables. They are constructing multi-billion-dollar, high-pair count submarine cables exclusively to connect their own massive geo-distributed AI data centers.
And the geopolitical and market implications of that are huge. They are basically hoarding the physical backbone of the internet. They keep the vast majority of the bandwidth for their internal proprietary machine learning replication traffic and only lease the scraps back to the wholesale market. The Tier 1 telcos are being starved of capacity because the tech giants have essentially privatized the ocean floor to feed their transformer models.
It is a total vertical integration of the global network stack, and bandwidth isn't the only resource being aggressively consolidated. If we look at the Wikipedia supply chain tracking, we are seeing a massive structural shortage in high bandwidth memory, or HBM, and standard DRAM.
This is the part that directly affects everyone listening right now. The scale of memory required to feed these Blackwell and Trainium chips is creating a black hole in the global semiconductor supply chain.
A literal black hole.
The OpenAI Stargate project alone reportedly locked in an agreement with Samsung and SK Hynix for 900,000 DRAM wafers per month. To put that in perspective, industry analysts project that single project will consume roughly 40% of the entire global DRAM output.
40% of the global memory fab capacity absorbed by a single concentrated AI initiative.
You can't just build a new factory overnight.
No, you cannot suddenly spin up a state-of-the-art memory fab. They take years to build and yield properly, so that 40% has to be cannibalized from other sectors.
Exactly. Which is why we are seeing persistent warnings about the cost of consumer electronics. The silicon allocation that was supposed to go into smartphone RAM, automotive infotainment systems, and standard laptops is being aggressively outbid by the hyperscalers.
They're just paying more to jump the line.
The reason your next smart device might be more expensive, or feature less base memory, is directly tied to a server rack sitting in an AI facility in Indiana. The global supply chain is being fundamentally rerouted.
It is a massive macroeconomic reallocation. And to understand where all of this hardware, memory, and fiber is physically going, we need to look at the McKinsey data, which brilliantly breaks down the structural split in the AI workload.
Training versus inference.
Right. The industry is effectively bifurcating into two distinct operational phases, training and inference.
And these two phases require completely different real estate strategies. Let's break down the tale of two data centers. Let's start with training. Training is the initial compute-heavy process of feeding trillions of parameters into a model so it can learn the statistical relationships.
The heavy lifting.
Right.
Yeah.
Because it is a massive, highly structured batch process, it is relatively tolerant of latency. You don't need a training facility sitting in downtown Manhattan.
Correct. Training centers are becoming the heavy industry steel mills of the digital age. They are enormous, gigawatt-scale campuses built in completely remote areas. They require racks pulling 100 to 200 plus kilowatts each.
So they go where the resources are.
Therefore, the site selection criteria are strictly governed by three things: the availability of massive, uninterrupted transmission-level power, cheap land, and robust water rights for the cooling towers. You build them where the resources are, not where the people are.
But inference is the exact opposite. Inference is the application phase. It's when the trained model is actually answering your prompt, generating an image, or reacting to a sensor. By 2030, the McKinsey report projects that inference will constitute over 50% of the total AI workload.
It becomes the dominant compute action.
Inference is incredibly sensitive to latency. If an autonomous system or a financial trading algorithm pings a model, it needs a response in milliseconds.
Which dictates that inference centers must be located at the edge, geographically proximate to the end user or the corporate network peering points.
Right next to the cities.
These facilities don't need gigawatt scale. They utilize racks drawing a more manageable 30 to 150 kilowatts. But they must be embedded in major metropolitan and Tier 1 markets to eliminate the speed of light delays inherent in fiber transmission.
And this creates an absolute real estate bottleneck in major markets. The McKinsey data highlights that time to power is now the ultimate defining metric for infrastructure development. You can have the $30 billion SPV, you can have the Blackwell allocation, and you can have the hollow core fiber, but if you can't plug it in, you have nothing.
Power is the ultimate gatekeeper.
In highly saturated Tier 1 markets like Ashburn, Northern Virginia, the queue for grid interconnection is staggering. We are looking at lead times of 36 months, sometimes up to 60 months, just to get a data center energized.
Hyperscalers are no longer optimizing their partnerships based strictly on cost per kilowatt. They are optimizing based entirely on speed to market. They are prioritizing developers and utilities who have already secured the zoning, the substations, and the environmental permits. The physical grids simply cannot move at the pace of software development.
So what does this all mean? We have massive capital deployment, we have custom silicon hitting exaflop of compute, we have fluid dynamic cooling retrofits, and we have Tier 1 real estate being consumed at an unprecedented rate.
It's a perfect storm.
But every single element of this multi-trillion-dollar vision requires one fundamental input: electricity, and we are rapidly running out of it.
If we connect this to the bigger picture, we are on a direct collision course with the power wall of 2027.
The power wall.
The Morgan Stanley Institute report on energy demand is arguably the most critical piece of intelligence in this entire stack. Global power consumption is surging at a rate we haven't seen in decades. Driven almost entirely by the AI infrastructure build-out, aggregate energy demand is projected to rise by more than 1 trillion kilowatt-hours per year through 2030.
1 trillion kilowatt hours. Let's ground that number for the audience because a trillion of anything is hard to visualize.
It's immense.
To support this growth, AI data centers are going to require an additional 90 to 126 gigawatts of baseload power capacity by 2030. That means the annual power demand for AI compute alone will equal the entire energy consumption of the country of Canada.
The whole nation's worth of power.
Or, if you prefer, it will comfortably surpass the power demand of the entire state of California. And that is just to run the servers and the cooling loops.
And this demand shock is hitting a grid that has suffered from years of deferred maintenance and structural underinvestment. Grid operators and developers are explicitly warning of severe systemic power shortages, manifesting by 2027 and 2028.
That is right around the corner.
The transmission infrastructure was modeled for slow, linear population growth, not the sudden vertical integration of gigawatt-scale compute loads.
And the political friction this is creating is intense. Because the AI sector operates on a 12 to 18-month product cycle, and the power grid operates on a 10-year permitting cycle, the clash is inevitable. And looking at the sources impartially, the regulatory responses are highly fractured.
Very fractured.
On one hand, data centers currently rely heavily on natural gas, which accounts for roughly 40% of their electricity. You have agencies like the Federal Energy Regulatory Commission, FERC, pushing through orders that allow data centers to co-locate and connect directly to power plants, essentially bypassing the standard grid interconnection queues.
Yes, and at the executive level, you see sharply contrasting approaches. You have the Trump administration policy maneuvers that paused certain offshore wind projects, which some analysts note disrupted potential renewable pipelines for these facilities. While simultaneously, the administration's energy secretary has advocated for unretiring obsolete coal and gas plants explicitly to meet the AI demand.
And on the other side,
Conversely, you have frameworks established by the Biden administration aimed at bolstering broader energy resources to secure AI leadership. The policy landscape is incredibly volatile.
we want to make it clear to the listener that we are not taking a stance or endorsing any of these specific political viewpoints. We are just impartially reporting what is in the source material, because this push and pull is drastically affecting the supply chain.
Exactly, it's a regulatory tug of war.
And the pushback from the legislative branch and local communities is equally fierce. You have Senator Bernie Sanders floating proposals for a federal moratorium on new AI data center construction until the grid strain can be properly evaluated.
A complete pause.
You have the independent monitor for the PJM interconnection, the massive regional transmission organization in the eastern U.S., warning that the grid's reserve margins are deteriorating and they simply cannot support the influx of data center loads.
The grid operators are sounding the alarm.
And critically, at the municipal level, standard consumers and small businesses are seeing their home utility bills spike, and they are directly attributing those rate hikes to the massive infrastructure costs required to support these localized AI facilities. It has become a highly charged, systemic political flashpoint.
Which is forcing the hyperscalers to completely abandon their reliance on public utilities. They are realizing that if they wait for the traditional grid to catch up, they will lose the AI race.
They can't wait 10 years for a permit.
The new mandate across the industry is bring your own power. We are seeing an incredible pivot where technology companies are vertically integrating into energy production.
The stopgap solutions are massive. We are seeing reports of developers securing 100-megawatt mobile natural gas turbines, essentially jet engines mounted on trailers, just to provide islanded power to these sites. They are building their own highly complex off-grid microgrids.
Whatever it takes to get the power.
And the long-term play is entirely focused on nuclear. Microsoft, Google, and Amazon are pouring billions of dollars into small modular reactors, or SMRs, and signing agreements to bring decommissioned nuclear plants back online.
They are transitioning from being passive ratepayers to becoming active primary utility co-developers. The capital markets are watching this energy transition closer than the silicon advancements because the entity that successfully solves the baseload energy bottleneck will command enormous sustained market value.
Power is the new gold.
But the terrestrial constraints, securing the contiguous land, acquiring the water rights, navigating the decade-long NRC permitting process for nuclear, and surviving the local political opposition are tightening incredibly fast. The physics of Earth are becoming a hostile environment for the scaling laws of AI.
Which leaves us with one final, deeply provocative thought for you to explore on your own. If the Earth's grid cannot generate the gigawatts fast enough, if the local politics prevent the zoning, and if the thermal density of these racks continues to fight the atmosphere, where do we go?
It's the ultimate question.
The Wikipedia updates reveal the ultimate, desperate, yet entirely logical conclusion that the hyperscalers are actively pursuing right now: the orbital data center.
It is the absolute bleeding edge of the infrastructure roadmap space.
We're seeing reports that Jeff Bezos, Elon Musk, and Sam Altman are actively researching and in some cases deploying early-stage capital into orbital compute architecture. It sounds like pure science fiction, but let's look at the math.
The math makes a strange sort of sense.
In low Earth orbit, you bypass every single terrestrial bottleneck we just debated. You have infinite zero-cost real estate. You have the absolute zero vacuum of space to manage the intense thermodynamics of exascale clusters. And most crucially, if you position the arrays correctly, you have unfiltered, uninterrupted, 24/7 access to pure solar energy without atmospheric degradation or day-night cycles.
The logistics of payload delivery and orbital maintenance are undeniably massive, but a company backed by NVIDIA called StoreCloud is already running proof-of-concept AI training models in orbit right now.
They are already up there.
When the economic incentives of artificial general intelligence are modeled as super exponential and terrestrial physics become an insurmountable hard barrier, moving the heavy compute infrastructure off-planet transitions from a theoretical concept to a mathematically viable, heavily funded engineering goal.
The economics of AI are literally forcing us off the planet. So tonight, when you walk outside, I want you to look up at the night sky, look at the stars, and wonder if, In the very near future, the next time you pull out your phone and ask a complex question, the neural network computing that answer isn't sitting in a server farm in Indiana, but is quietly orbiting in the vacuum of space powered directly by the sun. Thank you for taking this deep dive with us today. Keep questioning the physical reality behind the digital world, and we will catch you on the next one.